kinematics, we study the motion of an object where we get different relations among the motion variables like displacement, velocity, acceleration and time. You might remember the equations of motion for constant acceleration. The simplest state of object's motion are the object at rest or in uniform linear motion. If an object is in uniform linear motion, then it means it's moving with constant velocity. And the constant velocity means the object is moving with constant speed in a fixed direction. Do you think you need a net force? Net force means an unbalanced force to keep an object in the state of rest or in a state of uniform linear motion. Think about that. The answer to both of these states of motion is no. As per Newton's first law of motion, in an inertial frame of reference, everybody continue in its state of rest or uniform motion in a straight line unless acted upon by a net external force. Or in other words, if an object is at rest or moving with a uniform linear motion, then the net force acting on that will be zero. The change in the state of rest or uniform linear motion results because of a net external force acting on that object. The external force caused by an interaction with an object other than itself. This interaction between objects may be because of contact or non-contact forces. Contact forces are normal force, friction force, tension force, spring force, etc. While non-contact forces are like gravitational force, electrostatic force or magnetic force. To accelerate an object, you need a force. To retard and stop an object, you need a force. And even to change in direction of motion, no doubt you need a force. So to move, stop, accelerate, retard or change in direction of motion of an object, you need a force. This shows the tendency of an object to resist the change in its state of rest or motion. This tendency to resist the change is known as inertia of that object. Every object which has mass has inertia. More mass means more inertia, and more inertia means more resistance to change in its state of rest or motion. In other words, Newton's first law of motion is the law of inertia. So an object remains in rest or in uniform linear motion because of its inertia, and for that it doesn't need any net force. Whenever there is a net force, the object accelerates, or in other words, any accelerated motion is because of the net force acting on that object. In mathematical form, if sigma f is 0, that means the acceleration is 0. Or we can say the change in velocity is nil. It means the velocity is constant. In the case of mechanics, we assume an object as a particle and all the forces are working on that. So now when sigma f is 0, as per first law of motion, the particle may be at rest or may be in uniform linear motion. In both of these conditions, particles said to be in translational equilibrium. For example, book on a table. The weight of the books is balanced by the normal force by the table on these books. So here the forces are balanced, or the net force on the book is 0, and this is known as equilibrium of rest. Now other type of equilibrium is constant velocity. In this case, the object is moving with a constant velocity where the forces in vertical and horizontal directions are balanced. So the net force on this object is again 0. And this type of condition is known as equilibrium of motion. Or we can say the particle is in equilibrium. In general, if there are n forces acting on a particle and if a particle is in equilibrium, then the vector sum of these forces is equal to 0. In the case of two forces, F1 and F2, F1 is equal in magnitude of F2 and in opposite direction. While in the case of three forces, F1, F2 and F3 in equilibrium, the resultant of two forces F1 and F2 is equal and opposite to the third force vector F3. Also from the triangle law of vector addition, we know that the three concurrent forces are in equilibrium when they are represented by three sides of a triangle taken in same direction. Now let's check out couple of real life examples to understand the application of Newton's first law of motion. The first example is a coin on a smooth piece of cardboard falls into the glass when we strike the cardboard suddenly with a finger. In this case, initially both cardboard and coin are at rest. There is no net external force on any of these two. But when you strike the cardboard, you are putting a net external force on the cardboard, and because of that it moves out. The coin, which was in the state of rest, want to remain at rest because of its inertia, or as per Newton's first law of motion. But now after removal of cardboard, there is no normal force on the coin which can balance the gravitational force of the earth on coin. So because of this, there is a net gravitational force on the coin in downward direction. And this net external force pull the coin in the glass. So here we saw an object at rest continue to be at rest in absence of any net external force. In this case, we assume that there is no frictional force or negligible frictional force in between the coin and the cardboard. Because of that, the coin do not have any horizontal force or the force in the direction of cardboard motion. Here the example number 2. When we are standing in a moving bus and driver stops the bus suddenly, we are thrown forward with a jerk. In this case, our body is moving with bus velocity and it wants to remain in the same status of motion because of its inertia, or as per the Newton's first law of motion. When the bus gets stopped, our lower part, which is in touch with the bus, suddenly getting stopped, but our upper body is still moving in the same direction. And since our body can deform, so our upper part falls in forward direction, and because of that we fall. And that's all we have for today's session. I hope you would have enjoyed. If you think you have learned something new today, then please click like button and put your comments in description box and subscribe us for similar type of videos. Thank you for watching. See you next time. Bye.